sometimes we're going to find heat written within a reaction. We need to determine if heat is released or absorbed in order to determine whether this is an endothermic reaction or an exothermic reaction. So let's look at an example like this. What you need to remember for this, now, one, we can see heat. Heat is going to be either a number or the word heat in the reaction. So you can see it right there, that 24.1 kilojoules. It might also be in joules. Or it could, again, it could just be the word heat. And we have to remember how to read the symbol that is the arrow. That arrow is a symbol for produces, yields, or forms. So the way we can read this reaction is we've got some carbon monoxide, iron 3 oxide. Those two are going to mix together to produce iron, carbon dioxide, and that much heat. So in this reaction, where heat is a product, delta H is going to be, or heat is going to be released. And that is because it is produced. It is a product. It is made from this reaction. And so this is an exothermic reaction. And so delta H is negative. Sometimes we just have to put that sign on delta H to tell us the direction that the heat is moving. Since heat is being given off in this reaction, for an exothermic reaction, delta H would have to be a negative number. Let's look at it if heat is on the other side of the reaction. So here we can see heat is a reactant. We have this 176 kilojoules of heat. It could be in joules, it could just say the word heat. And again, if we remember what an arrow stands for, what this reaction is saying is that calcium carbonate has to be heated in order to break down into calcium oxide and carbon dioxide. So that means that heat is absorbed in this reaction. It is a reactant. It's going to make things happen. Now, that absorbed heat is going into breaking old bonds or something like that, not into raising the temperature. So this is actually going to feel cold if you were to touch it, because it would be absorbing the heat from your hand if you were to touch the reaction vessel. So this is an endothermic reaction. And delta H would need to be a positive number, because again, we use the sign to represent the direction that the heat is moving. So that's how you deal with, okay, driving force of reactions. We're going to talk about the concept of a spontaneous reaction today. Now, a spontaneous reaction is one that just happens without us having to force it. We don't have to add anything extra, no electricity to force it, no heat to force it. It just happens. Now, it doesn't say anything about how long it takes. It may take 2 seconds. It may take 200 million years. As long as it just happens, it is spontaneous. Like rust. Rust happens over a long period of time. All right, but it's still a spontaneous reaction. If you chunk one of these chairs outside and leave it there, it will rust. It just takes a while. Now, our next topic will be rates, and then we'll talk about how long it takes. All right, but this one's just whether it will happen naturally or not. Now, there are 2 factors that will predict reaction spontaneity. Whether a reaction will just happen or not. One of them we've already discussed, and that is enthalpy, the heat content. Exothermic reactions are generally spontaneous, especially exothermic reactions that give off a lot of heat are generally spontaneous, but not always. The other one is the randomness of the particles in the system, and that is our entropy. I'll get to it. Okay, so enthalpy and reaction tendency. Now enthalpy, that's the one that has the H, so this is your delta H, your heat content. Majority of reactions in nature are exothermic. And because they give off so much heat, the products end up more stable and have less energy, less potential energy. The next one is entropy and reaction tendency. There are naturally occurring spontaneous reactions that are endothermic. So there's something else that drives it towards spontaneity besides giving off heat, because these have to absorb heat. Ice melting is an example of that. And what is driving that particular reaction towards spontaneity is that it's becoming more disordered. All right. Entropy, which is S. I know there isn't an S anywhere in that word. It's the measure of the degree of randomness, or I like to read it as disorder. And if you over-exaggerate the S in disorder, it helps you remember that entropy is delta S, or change in entropy is delta S. It's disorder. And you can always read it that way, as disorder. Entropy is the basis for the chaos theory, where, and in the chaos theory is that everything in the universe is going toward chaos. It is based off of this idea of entropy. And nature does prefer things to become more disordered. You know, if your mom makes you clean your room, and so you do, and then the next day, what does it look like? Yeah, before you cleaned it. It looks exactly like before you even cleaned it, all right? That's entropy at work. Now, you can try and use that as an excuse. My mom didn't buy it. I was like, Mom, it's just entropy. She's like, I don't care. We're fighting against it again today. Okay, now it has units. Kilojoules per mole Kelvin. Kelvin does play a role in this. Why would temperature affect the amount of disorder? Yeah. Ah, good. Kinetic molecular theory. As temperature goes up, the particles are moving faster, so things are going to get more disordered more quickly. Okay, so here's the trick with entropy. It increases as you go from less moles to more moles. All right, so you know that street game where they have the cups and a little ball, and they put the ball underneath one of the cups, and then they mix them up, and you have to find which cup has the ball underneath it? Now, in the street game, they play it with 3 cups. Well, imagine if you only had 2 cups, and I put a ball underneath.
and I mix them up. You could probably win that game, couldn't you? Because there's only so many ways I can mix up two things. Here. You can probably watch that, all right? But with three, it can get way more disordered, all right? It makes it a more challenging game, and it is a street game, so it's one that people most often lose. Plus they cheat, but whatever. All right, so less moles, more moles. The more moles you have, the more disordered things can be. All right, so entropy increases. The other one is entropy increases as you go from solid, because particles can't move around, all they can do is vibrate, to a liquid. They're still held by their attractive forces, so all they can do is move over and around one another, to a gas that has no attractive forces and is zooming all over the place. The entropy of a pure crystalline solid is 0. It is perfect order. Increased heat increases molecular motion, and that's why Kelvin temperature is a part of the units for entropy. Okay, more signs to remember. We know delta H negative is exothermic. Delta H positive is endothermic. Well, now we have delta S, our change in disorder. So if it is negative delta S, we are moving toward more order as the reaction proceeds. Positive delta S. Now remember, you can always read delta S as disorder. So positive disorder, you're going to more disorder. All right? So we're going to try and predict the sign of delta S for these two reactions. So let's look at A. In this particular one, we have calcium carbonate going to calcium oxide and carbon dioxide. What we have to look at here is the amount of disorder. We have a solid going to a solid and a gas. Are we moving toward more disorder or more order? More disorder. A gas is way more disordered than a solid is. Okay, so our sign of delta S is going to be positive because we're moving toward more disorder. Good. All right, if we look at B, I have sulfur dioxide and oxygen gas going to sulfur trioxide. They're all gases, so we can't use that one. So we have to go with this other one. Entropy increases as we go from less moles to more moles, and it's really of gas. We're going to get our moles here by coefficients. It tells us the relative number. So I have 2 moles of sulfur dioxide, 1 mole of oxygen gas, so that's 3 moles on this side. And on this side, we're going to 2 moles. All right, so are we moving toward more disorder or more order? More order, so delta S is negative. Let me try others. Okay. Is delta S going to be positive or negative? going to more disorder because we're going from a solid to a solid and a gas. All right, let's look at this next one. What's the sign of delta S? Negative. We're going to more order because we're going from a liquid to a solid. Okay, more order, so delta S is negative because we're going from 4 moles, 1 plus 3, to 2 moles. Positive. A solid, those ions can't move around, and now if it's an aqueous solution, those ions can move around. There's more disorder there. Positive. We're going to more disorder because we're going from a solid to the liquid. More disorder, so it is positive. Right? That's solid to a gas. It is called what? Sublimation. Good. Good. All right. Do you feel okay with those? Okay. On your homework, you will have some problems dealing with figuring out the sign of delta S. Okay. Okay, so nature likes negative delta H, exothermic reactions, especially if that's a big exothermic reaction, and positive delta S, more disorder. If a reaction has those two things, it will always be spontaneous. If it has the opposite of these two things, if it's an endothermic reaction going to more order, that will never be spontaneous. That will never happen on its own. That's something we would have to force. Okay? One of my students said it this way. So, nature likes a hot mess. Yes. Okay? Like a hot mess. All right.